Hello. In this video, I will go over the priority queue. I'll have a look at what it does and then I'll examine it in a little bit more detail. The big difference between the priority queue and a queue is that a priority queue is not first in, first out. Its items are ordered in a different way. So it doesn't go into a list and then it keeps that position in the list. Its position in a list can change according to its priority. Because items have a priority attached to them, each time you insert something, the list would have to rearrange to make sure that the priority is at the front of the queue. So if we did that with a list, we would have big O of n log n. So instead, we use a binary heap, which gives us O log n, which is quicker. This is to give you an idea of what's going on in the priority queue. So if you remember with a queue, you would insert things into here and they would move along until eventually they were popped out. So they were first in, first out, because the first one in would obviously be the first one out. This is arranged in a different way. So we use a binary heap to give some values their place in the queue. So if we imagine that these values are key values and they're the priority. So two here would be the highest priority. And if we say that, where is it, 52 is the lowest priority, and you can see that 52 here is in the wrong place. So, and they're all mainly in the wrong place. If we go from this end to this end, they're in the wrong place. But remember that when we look at our list here, the high priorities will be at the front of the queue. So I'm going to take numbers from this list. I'm going to take numbers from this list and pop them into the binary tree so that you can see what's going on. So you have the binary tree. This is the root, and these are children. If they had no children, then they would be leaves. So we're going to insert, and we'll start off with the root node because we haven't got anywhere else to put it. So we start with 10 here. And we pop that in. And then we pop in 8. And we always go from left to right. So the next one to be inserted will be here. And then the next one to be inserted will be here. And then here. Okay. Now, because these are the only two in our tree, we want to make this this root node here the minimum value. So we do the comparison and we discover that 8 is less than 10. So they swap round. Now, if we insert another value, we've got 12 there. Eight is less than 12, so it can stay where it is. We insert another value, 4, that will be inserted over here, because we go from left to right. We do the comparison and we see that 4 is less than 10. So they swap round. Here we see that 4 is less than 8, so they swap round. Now we can move on to the next value. That's 52. The next space to go is here. And 52 is in its right place for now. 13 is inserted in here. That's okay for it to be there. And 2 is then inserted in here. We can see that 2 is less than 12. So we can swap that round. We can see that 4 is greater than 2. So we swap that round. We have no more values to insert into our tree. So now we're going to start removing them. And we remove from the root. So if we take that out and we pop that out into a list. 2. So we remove that. Now we have an empty space at the root. So what we're going to do is we're going to take this value here and copy it to there and then delete this entry. Now, going from left to right, we can see that 8 is less than 12. So we swap those round. Then we do more comparisons and we can see that 12 is greater than 10. So we swap those round. The 8 is greater than 4. So 4 swaps there. Now we're finished sorting. So we can remove root again. And that goes over. We have an empty space. So next we move to this guy. Because when we're inserting, we go from left to right, and when we're deleting, we go from right to left, and when we're removing, we go from the root. So this 13 is now the next one to be copied to the root. Then we delete this entry. Now we can start ordering again. 13 is greater than 10. So we swap them around. "13 is greater than 12, so we swap those around. And 52 is greater than 12, so we leave that where it is. 8 is less than 10, so we swap them around. And now there's nothing else to do, so we can remove 8. Now we copy 52 and delete the entry. 52 is greater than 12. So we swap them. 52 is also greater than 13. So we swap them. 12 is greater than 10, so we swap them around. We can't do any more, so we remove 10. And then we find that we're sending 52 back to the root. Excuse me. Now we delete the entry. 52 is greater than 13. So they swap around. And 13 is greater than 12. So they swap around. And now 12 can come out because there's nothing else to do. So we remove 12. And now we put 13 into the root and delete that entry. 13 is less than the only other entry, 52, so nothing else happens. We can remove 13. 52 is then copied to the root and its entry deleted. There's nothing to compare it to, so it's removed from the tree. And we are left with this list here, with T, low, and high. Height. I don't know why I said height. High. If they were in our list here, we would have 52, 13, 12, 10, 8, 4, and 2, with 2 obviously being the highest priority. So we still have NQ and DQ. The big difference is, rather than putting things into a list, we put them into a binary heap. And the binary heap has certain properties. So you can have like a min heap or a max heap. I've just done a min heap. A max heap would be putting the making sure that the maximum number goes to the root rather than the minimum number. I'll do a lot more on binary trees and binary heaps and trees and this type of ordering in future videos. But for now, I just want you to see how the priority queue works. It's going to use a binary tree, or binary heap, I should say, because O log n is going to be better than if you're just doing a sort in this list. If we were to just take this list here and then just sort it as a list, the best we could do would be O n log n. So that's why we use this binary heap.
If you liked this video, give it a thumbs up and try out one of my other videos.